This is Module 3, Proportional Reasoning, part of a professional learning series for Foundations of Algebra teachers. We encourage you to follow along and construct the visual representations discussed within this session. Feel free to pause at any time to share your thoughts, ideas, and questions with your colleagues. This professional learning series is designed to explore the foundations of algebra content and strategies for teaching that content by looking at the big ideas within this module. The first of the 4 big ideas in this module is that ratios are multiplicative comparisons. This is a key idea that students need to develop. Often, ratios are addressed in a superficial manner, with students recording the symbols 7:10 to tell the ratio of, for instance, cat to dogs. Ratios should be taught as relations within contexts that involve multiplicative reasoning. Sometimes, to put students at ease, teachers will tell students ratios are just like fractions. And while ratios and fractions are similar, there are important distinctions that students should be able to make. Here are 3 examples to help with developing the understandings of the overlap of these 2 concepts, as well as the differences. Which of these relations are ratios, and which are fractions? Are there any that are both? Pause the video here and discuss this with your team. What was your conversation like? Did you construct viable arguments? Did you critique each other's reasoning? Let's see how you did. The first example is a ratio, not a fraction, because fractions are not part-to-part ratios. The second example can also be thought of as 3/10 of the pets are dogs. Since this is a part-to-whole ratio, it is both a ratio and a fraction. The last example is a fraction of a length and is not a ratio because there is not a multiplicative comparison. Ratios can actually be thought of in 4 ways. Part to part, and in this type of ratio, one part of a whole, like 8 red counters, can relate to another part of that same whole, 5 blue counters. This can be represented as 8:5, or a ratio of 8:5, not 8/5, because it is not a fraction, even though it can be written with that fraction bar. We see part-to-part ratios in the diagonal of a square to its side as the square root of 2. The slope of a line is a ratio of rise for each unit of horizontal distance, and when finding the odds of an event occurring. Part-to-whole ratios can be written as part of a whole, for example, 8 red counters to the whole group of 13. This can be thought of as 8/13 of the counters are red, a fraction. Percentages and probabilities are part-to-whole ratios. Ratios as quotients. If you can buy 10 candies for $1, the ratio of money for candies is $1 to 10 candies. The cost per candy piece is 10 cents, or the unit rate. And ratios to rates, miles per gallon, flowers per bouquet, and cans per case, are all rates. Rates involve 2 different units and how they relate to each other. Feet per yard, centimeters per inch, and milliliters per liter are also rates. A rate represents an infinite set of equivalent ratios. There's 2 ways to think about ratios. As a multiplicative comparison, consider the 2 pencils on the left. The lengths of the pencils are 6 inches and 8 inches. At this point, it's common to ask for a ratio of the pencil lengths. When students tell us 6 to 8, we assume they know ratios and then we move on. This is a very low-level question and does not communicate the relationship between the measures of the pencils. Pause the video here and discuss with your team how these pencils could be compared multiplicatively. Did your conversation include multiplicative relationships like these? The short pencil is 6/8 as long as the long pencil, or 3/4 as long. Or the long pencil is 8/6 as long as the short pencil, or 4/3, or 1 1/3 the length. The multiplicative relationship is the ratio, not the symbols, and involves us asking questions like, what fractional part is one thing of another? Or, how many times greater is one thing than another? The other way to think about ratios is as a composed unit. And this refers to thinking of a ratio as 1 unit. This is a key development milestone for students. Unitizing is not a new idea for students, but every time it shows up, students need time to grapple with it before owning the idea. If packs of crayons are 4 for $1, you can think of this as a unit as well as multiples of this unit like 8 for $2, 20 for $5, etc. And we can also partition the composed unit to 2 for 50 cents and 1 for 25 cents. Any number of packs of crayons can be priced using composed units. It's important for students to be able to apply both types of ratios. In the cupcake problem, the context allows for students to first chew on the idea of composed units and then multiplicative comparison. Pause the video here and try this problem yourself. Give yourself some alone time and some together time with this problem. Did you all attack this problem in the same way? Did you use materials like color tiles at any point, or drawings? If no one used materials or drawings, pause the video now and take a few minutes to see if you can make sense of this problem in this way. Given options to use tools or drawings, students will make sense of problems like this and develop these two ways of thinking about ratios. The second big idea is about equivalent ratios and how the comparisons involve multiplication and division rather than addition and subtraction. Problems like these two can be problematic for students. Sometimes classes as a whole will say they're both the same. Each set has 2 girls. It's important when helping students to develop multiplicative thinking that you run through these problems as a student. Jot down all possible arguments students might give, and then think of some least helpful questions, as opposed to leading questions, to ask and write those down as well. This is much easier when it's done before teaching the lesson. And you may not think of all the things that students might say, but it sure helps to have some questions available when the lesson's in progress. Pause here and discuss with your team what arguments students might make, even if the only one you expect is that they'll be adamant and say they both have 2 girls, they're the same, or they both have 3 circles, so they both have the same amount. Then take some time to write some least helpful, not leading questions to promote student thinking. Welcome back. Did you come up with more than one argument students might make? What were some of the questions you asked? Were they least helpful? Here are a few questions we thought up. What are some other ways to compare the sets? Mrs. Blank down the hall showed this to her class, and one of her students said one group definitely had more girls. What do you think about that? How could this student be thinking about these sets differently? Another way to start this activity might be to not ask which has more, but leave it open and ask, what do you notice? And then write down everything your students say. My guess is that someone will say the bottom group is half boys and half girls. That's the first step. For this next activity, we move students more to numeric strategies. Look at the cards. The task is to match cards where the ratio of objects is the same. It makes sense to think of these as boxes per truck rather than trucks per box. Pause the video and take a few minutes to try this, and then share your strategies. This is probably my favorite task for thinking with ratios and proportions. Please pause the video here and engage in this task, and then share your strategies. How many ways did your team find to determine which picture was lemonier? Did anyone use part-to-whole ratios? Did anyone use part-to-part ratios? Which one is lemonier? This task comes from illustrative mathematics. The great thing about this task is that it comes from a real ticket booth. You can see the picture at the link in the notes. And it also leads us to the next big idea. But first, take a few minutes to tackle this task and share the results with your team. The third big idea in this module is the idea of rates and how they represent an infinite number of equivalent ratios. A nice way to introduce this idea, after a lot of practice with reasoning about ratios like what we've seen so far, is with a graphing story. A graphing story asks students to graph what they see happening in a 15-second video. Students will need a sheet like this and a video, and all of these can be found at the link in the notes. If you have some of these sheets handy, grab some. If not, grab some graph paper and make it look like one of these graphs. Time is always along the x-axis, in seconds. The y-axis varies from story to story, but pay attention to the beginning of each video, and you can quickly jot down the meaning of and values on the y-axis. You can also pause the video for students. Here we go. Pause here to take some time to share your graphs and talk about any differences and similarities, as well as what students may do. Explorations of rate help students build the concept of slope, which describes the rate of change for a linear function. Conceptually, we're developing this idea that slope is the rate that shows how much y increases when x increases by 1. Try this. Take a look at these two lines. What do you notice? What do you wonder? Pause here and jot down all of your notices and wonders, and then share with your team. Are the lines parallel? What information would you need to help settle this? If only there was some way to count and see how much one line was rising. Maybe a tool, like a grid, would help. Here you go. Is there anything else you might want? Axes? How about some points? Is this helpful? Note, when doing something like this with students, it's best to give only the information that they ask for in order to foster a productive struggle. With this format, that's difficult for me to do with you here. So, are the lines parallel? If not, which line is climbing at a faster rate? And will they intersect above or below our field of view? If so, if they are parallel, how do you know that they will never intersect? So what about no slope and zero slope? These are two easily confused slopes And like many ideas in mathematics, contexts can help students distinguish between the two. Consider this story. You walk for 5 minutes at a rate of 1 mile per hour. You stop for 3 minutes to watch some ducks in the pond. Then you walk for 8 more minutes at 2 miles per hour. What will the graph look like for the 3 minutes you stopped? What is your rate when you stop? What if you saw this graph of a walking story? What would the vertical line mean? You traveled a distance without time passing. Remember, rate is based on a change of 1 in the x variable. Here, you traveled a good distance with no time passing. The fourth and final big idea for Module 3 is all about solving proportions in a variety of contexts through the use of reasoning rather than fixed procedures. Back in Module 2, we looked at some growing patterns. Here are 3 more. Do these growing patterns describe proportional relationships? Take a few minutes to discuss these patterns with your team. Graph them. What do you notice? Which are proportional and which are not? Revisiting concepts that are familiar contexts like this helps students understand the interrelatedness by giving students the opportunity to make connections. As you can see, A and B are proportional relationships, and C is not. Take a look at the graphs you made. What do A and B have in common that's not true for C? Discuss this with your team. Textbooks typically show students how to set up an equation of 2 ratios involving an unknown. The challenge we face as teachers is to teach ideas and reasoning rather than a quick and easy computation algorithm. Rather than tell students to cross-multiply, build understanding through visuals like a number line diagram seen here. This visual allows for multiple strategies to emerge based on student reasoning. For example, students may find the price of 1 pound of apples by dividing and then multiply that by 6. These steps can be shown on a number line itself. Another student may determine that the scale factor here is 1.5 and multiply this by 4. Each way gives you the answer. Try to solve this 3-act task by Andrew Stadell with your team using a strategy other than cross products. A link to all of Andrew's tasks can be found in your notes. A copy of a 3-act recording sheet adapted by Graham Fletcher can be found in the notes as well. Okay, you know the drill. Take a few minutes to jot down your notices and wonders and share it with your colleagues. The anticipated question here is, how long is that song? We'll use that question for the rest of our 3-act. Make your best guess estimate. In the next 5 seconds, write your best guess estimate. 5, 4, 3, 2, 1. Write down your best guess. Now, write an estimate that you know is too low, and write another estimate that you know is too high. Write your too high and too low estimates at the ends of a number line. Now, place your best guess estimate where you think it belongs on your number line. This is a nice benchmark to assess your students' understanding of the magnitude of numbers. Time for Act 2. Remember, our focus question is, how long is that song? What information do you need to answer this question? Since I can't wait for you to ask, let me show you an image. Try to use this information to answer the question, how long is that song? Pause here to give you and your team some time to solve this problem. How did you do? What strategies did you use? Are you ready to see the reveal? Before I show you, if you're off by a little bit, why might your answer be off by a little bit?
This one out.
How close were you? Discuss with your team, again, why your answers might be off. To pull all of this together requires 3 ideas. The first is differentiation. Think CRA, concrete, representational, abstract. And that doesn't mean for the first 3 days we use manipulatives, and then we put those away and never use them again. And now we're just going to draw pictures for 3 days, and finally we use an algorithm. All 3 must be included from the start, just like when we did the growth patterns in Module 2. The sketch is included the first time they investigate, but there's also an expression at the end. It may not be algebraic the first time, but students will work up to that understanding. Here are some tiered tasks for working with ratios and proportions. Students can work on the same standard with various levels of support. Students at all levels benefit from rich problems like how many fish are in the pond to start. To provide support for those below-level students, supplement with tasks such as the mixing colors from NZ Maths. Meeting with small groups is certainly beneficial. It can be overwhelming to schedule. The 2 slides that follow offer some suggestions about how to manage small groups so as to maximize student learning. This suggestion comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate you do not have to have a small class size to implement small group instruction. The Georgia DOE is not suggesting the Foundations of Algebra classes should be increased to 30 students. This suggestion comes from the Social Emotional Learning and Mathematics session from Global Math Department. It also lists a class size of 30 students to demonstrate that you do not have to have small class size to implement small group instruction. The Georgia DOE is not suggesting the Foundations of Algebra class sizes should be increased to 30 students. Let's keep the conversation going. The DOE has created a wiki space for high school teachers to engage in discussions about math teaching using the Georgia Standards of Excellence. Here, you'll find a forum to keep the conversation going, resources, and who knows, you might make a few friends. It's a call to action, and you are invited to make a difference. Access this online community here. And speaking of online communities, if you're on Twitter, please join us at the hashtag MTBOS. the Math Twitter blogosphere, where everyone has a voice and we all learn from each other. There are no dues and no applications. If you're a math teacher and you're on Twitter, you're in. If you're not on Twitter, then here's a reason to join. If you're not a math teacher, become one.